This other factor that helps determine spontaneity is entropy. Spontaneity is favored by an increase in entropy. In other words, most spontaneous reactions occur simultaneous with an increase in entropy. However, not all spontaneous reactions demonstrate an increase in entropy, i.e. have a value of delta S greater than 0. Entropy is a thermodynamic state function. However, it's not very easy to describe. Often it's described qualitatively as the amount of disorder in the system. Disorder, randomness, freedom. The more chaotic a system is, the greater its value of entropy. Disorder, randomness, freedom, these are all very qualitative terms. For a quantitative measure of entropy, we go to the Boltzmann equation. Entropy is equal to K, the Boltzmann constant, times ln of W. W refers to the number of microstates possible for a given set of conditions, a specific configuration of the location and energies of particles in the system. We'll see some simple examples shortly. Boltzmann was a controversial character. He spent his life defending this equation and sadly committed suicide before he could see experimental verification. However, he knew how to get the last words, inscribing his equation on his tombstone. Here's a quick illustration of microstates. Consider that we have two particles, and these particles can be distributed between two boxes. There are 4 ways these two particles can be distributed between the two boxes. We have them different colors so that we can distinguish between them. Both particles could be in the same box. There's 2 ways in which both particles can be in the same box, and there's 2 ways in which the two particles can each be in one box. These 4 different distributions correspond to 4 microstates. Now, this is a very simple example. We'll expand our example to 4 particles potentially distributed over 2 boxes. The number of microstates is going to correspond to 2 raised to the n power, where n is the number of particles. So we're going to have 16 different microstates. We will organize the microstates into groups that have similar distributions. The most probable distribution will be the one where the particles are equally distributed across the 2 boxes. There are 6 microstates associated with this distribution, so its value of entropy is going to be the largest. It has the largest value, W. High states of entropy are favored because they are the most probable. They have the largest number of microstates within that distribution. We can apply this to our previous example, where this microstate is highly improbable, where all the particles are contained in a single bulb. The most probable distribution, the highest entropy distribution, will be the one where the particles are equally distributed across both bulbs. We can draw a similar example with heat distribution. Initially, we see that there are 3 possibilities of 2 heat energy units in the same box. Once the hot object and the cool object come into contact, there are 2 possibilities. The first set of possibilities is that the heat content will be distributed equally across both boxes. And this first set of possible final states has 4 microstates. There's 3 microstates in the second set of possible final states in which both energy units are transferred to the second box. This first set of possible states is going to be the most probable as it has the greater number of microstates. It's going to have the greater entropy. In general, the most probable, the highest entropy state will be the one in which either the particles or the heat is evenly distributed throughout the container. This is when we have the highest value of entropy.